Welcome to the Explainer, builders. I am your chief architect, and today we are laying down the ultimate structural blueprint for Cambridge AS and A-level mathematics, specifically topic 1.4, circular measure. We are running this as a high-rise exam construction blueprint workshop. If you have been losing marks on those high-tariff trigonometry questions, or if those massive compound shape problems keep causing your final answers to completely cave in, you are in the right place. We are going to lock down an unshakable thesis foundation, erect load-bearing analytical arguments, and construct structural mathematical connections that can survive the most rigorous examiner's stress testing. So, put your hard hats on, fire up the digital drafting screen, and let's get straight to work. Right off the bat, a senior examiner makes the stakes incredibly clear. They stated, quote, "The difference between a B and an A-star in mathematics often comes down to how well you understand 1.4 circular measure." Think of this as the ultimate site inspector telling you exactly where buildings fail. Mastering this topic is the foundation that prevents your final grade from completely collapsing. Why? Because circular measure isn't just some isolated standalone topic you can afford to gloss over. It's the core structural column that supports advanced trigonometry, calculus, and complex mechanics later down the line. If your fundamental understanding of radians, arc lengths, and sector areas has cracks in it, the rest of your A-level mathematics skyscraper will inevitably lean, crumble, and fall. We literally cannot afford to lay bad cement here. Before we start pouring the concrete on these equations, let's look at the master blueprint for today's structural exam workshop. We're moving through 6 zones. 1. The foundational challenge. 2. Laying core mathematical principles. 3. The procedural blueprint. 4. Deconstruct, solve, and evaluate. 5. Examiner stress tests. And finally, 6. The final site inspection. Section 1, the foundational challenge. Let's step into the blueprint room. Our primary objective here is building an unshakable mathematical thesis. In the blueprint room, we look directly at the building regulations. These are the exact assessment objectives enforced by the Cambridge Examiner reports. And the number 1 regulation is this: you must prioritize analytical depth over superficial breadth. Your assessment framework requires logical, structured reasoning where analytical depth acts as the heavy steel frame of your answer. Let me tell you about 2 junior builders I had on site recently, Alex and Sam. Alex is the kind of builder who loves superficial breadth. He gets a question, panics, and tries to stack up 50 heavy bricks of raw mathematical facts. He dumps every single trigonometric identity he can remember onto the page without checking if the steel frame of the specific question can support that weight. He thinks he's showing off how much he knows. But Sam knows that if you build a descriptive structure instead of an evaluative one, the building collapses instantly under the weight of the mark scheme criteria. Analytical depth means looking at the command stress points of the prompt, selecting the exact right beam, and welding it perfectly into place. Top-performing structures are built by taking a connected, conceptual understanding and seamlessly transferring it to completely unfamiliar exam contexts. When you open up that exam paper, the construction site isn't going to look like the perfectly flat, easy diagrams you practiced on in your textbook. You are going to be handed a completely unfamiliar, bizarrely shaped plot of land. It might be a wild compound shape involving multiple intersecting circles, shaded regions, and hidden triangles. If you just memorized routines, you're going to freeze. But if you have mastery of fundamental principles, you don't panic. You look at that unfamiliar context, and your brain traces a flashing grid, showing exactly where the columns must be aligned. You immediately identify the underlying structural geometry. You see the hidden right-angle triangles, you spot the intersecting sector areas, and you know exactly how to lay the groundwork. Moving on to Section 2, laying core mathematical principles. Let's look at the raw materials you must master to lay down this unshakable foundation. We are talking about absolute precision with your circular measure formulas, calculating with radians, finding arc length where S equals r theta, and determining sector area where A equals 1/2 r squared theta. These are your load-bearing columns. They are required to support your entire response. But here's where the ironwork peer debate happens on the drafting board. Alex says, "Chief, I've got the formulas memorized. I can just slap them down." Sam rightly argues back, "No way, Alex. If you try to put up those shiny glass panels before you cement the foundational columns, you're going to fail." And Sam is completely right. Just writing down the formula gets you absolutely 0 marks. If you don't look at the command words, you're doomed. If the exam question is given in radians, but your calculator is still in degrees because you forgot to switch it, I don't care how beautifully you wrote out S equals r theta. You just poured toxic cement. Every single calculation that follows will be structurally compromised, and the examiner will tear the whole building down. Let's move into Section 3, the procedural blueprint. Having the raw materials isn't enough. We need to actually erect the scaffolding using a strictly enforced procedural framework. Every single calculation you make must rigidly follow this standardized 5-step sequence, or your structure is going to collapse midway through the exam. First, identify key elements. Survey the land. What is the radius? What is the angle? Is the domain exclusively in radians? Second, apply relevant principles. This is where you grab the correct formula from your toolkit depending on whether you're framing a perimeter or an area. Third, execute your analysis with clear working. Do not skip steps in your head. You have to bolt everything down on paper. Fourth, verify your results. Does this number actually make physical sense? If you calculate a shaded region and it's mathematically larger than the entire circle it sits inside, you have a massive structural flaw. Catch it now. And finally, step 5, present in the appropriate format. Lock it down with the correct significant figures. Furthermore, your presentation has to follow strict building codes. This means you must enforce proper headings, accurate terminology, and totally clear annotations. Imagine the Cambridge examiner as a highly critical city building inspector walking onto your site. If there are no clear annotations, they simply cannot tell which part of a complex compound shape you're actually calculating. Are you finding the area of the minor sector or the major sector? If you don't use correct terminology, or if your working format is just a chaotic, spiraling scribble across the page, they literally cannot award you the points. Your working out needs to be so logically laid out that I could walk onto your site, pick up your blueprint, and know your exact process without having to ask you a single question. This brings us to a massive structural debate, the method mark strategy. You must thoroughly understand that examiners award heavy marks for your systematic processing, not just the raw final number. Alex always tries to rely entirely on a raw final answer. He punches everything into his calculator in one giant go, writes down a single decimal, and hopes for the best. That is a massive gamble. If his finger slips and he hits a 4 instead of a 5, he loses every single mark. The entire building falls. Sam, however, uses the method mark strategy. Sam earns points for demonstrating the systematic process line by line. Even if Sam makes a tiny arithmetic error on the final floor, the examiner sees the reinforced steel frame of their logic. They see the correct formula, they see the correct substitution, and they award the method marks. Document your process and you protect your grade. Section 4. Deconstruct, solve, and evaluates. Site inspection. Right before we pour this next layer of text concrete, I need you to pause. We are hitting a critical phase. And before we secure this high-squaring paragraph framework, make sure your construction line is permanently reinforced. I highly recommend you subscribe to the Ace the Exams channel right now and turn on all notifications to receive our weekly structural grade upgrades. Whether you are building an IGCSE foundation or setting up an A-level skyscraper, having that constant feed of architectural blueprints is your primary grid for success. Okay, let's get back to the matrix. With the scaffolding up, it's time to frame the critical analysis using this heavy-duty 3-phase load-bearing structure. When you hit a complex problem, you move smoothly from deconstructing to solving to evaluating. First, deconstruct. You have to break the given info into logical steps. Find the hidden triangles inside the circles. Next, solve. Execute systematically with crystal clear working. And finally, evaluate. This is where you check the reasonableness of your answer and justify your mathematical recommendations. Top-scoring candidates reinforce their structural framing through pure evaluative thinking. You have to question assumptions, consider different geometric perspectives, and justify every single analytical decision with rock-solid evidence. Let's say you're mid-built, and your evidence beam suddenly fails to latch onto the main thesis column. You're looking at a triangle inside a circle, and it kind of looks like a right angle. Alex would just assume it's 90 degrees and start hammering away. Sam knows better. Sam questions the assumption. Can we actually prove it's a right angle using circle theorems? Does the line pass through the center? You cannot guess on a high-rise site. You must justify that decision numerically before you lock it in. Section 5. Examiner stress tests. Let's see how your building holds up. We are now entering the interactive viewer rebar stress test phase. I want you to imagine a 60-second visual countdown timer ticking on your exam clock. The Cambridge examiner is dropping a massive weight onto your final answer to see if the structure holds. According to the principal examiner reports, these are the top 3 reasons student foundations instantly collapse under grading pressure. Failure number 1, wrong approach for the specific context. This is like trying to use a blowtorch to cut wood. You're using degrees when the domain mandates radians. Boom, collapse. Failure number 2, forgetting to check format and presentation. The prompt specifically asked for an exact value, and you gave them a rounded decimal. You didn't follow the blueprint. Boom, collapse. And failure number 3, answers are not specific to the context given. You calculated the entire area of the sector, but the question actually asked for the perimeter of the unshaded region. You built a great roof, but on the completely wrong house. The classic trap here is pouring a generic block of cement. A generic foundation is when you memorize standardized routines that are completely disconnected from the actual prompt in front of you. You just start doing math without a plan. You must replace that with a reinforced foundation. A reinforced foundation means every single evaluative point, every single arc length you calculate, and every single sector area you derive is linked directly and explicitly back to the given scenario. You extract the single most high-yielding core metric needed for construction, and you build from there. If the question is about a running track modeled by semicircles and rectangles, your final concluding sentence better directly reference the perimeter of that specific track, not just an abstract variable x. Section 6. The final site inspection. We are nearing the end of the build. It is time for the final site safety audit before you officially sign off and secure this framework. As I mentioned earlier, you need to make sure your construction line is permanently reinforced by subscribing to ACE the exams and aggressively practicing those past papers. Watching this blueprint workshop is step 1, but you are not a master builder until you actually get your hands dirty. You have to pull up those high-tariff past papers, grab your calculator, and physically lay down the mortar yourself. Practice is what upgrades your structural grade week after week. So, as we pack up the blueprint room for today, I leave you with this final critical site inspection question. As you head into your next past paper, ask yourself honestly, is your mathematical foundation truly structurally sound enough to survive the examiner's ultimate stress tests and build that A-star? Next time you see a massive compound shape, are you going to panic like Alex and just throw down random formulas? Or are you going to step up like a master architect, spot the command words, deconstruct the geometry, and build a flawless, unshakable argument? The tools are right in front of you. Now go build it.